going to discuss EM waves in matter. So in case of material, we can write our Maxwell equations and other previous results just by replacing mu naught to mu and epsilon naught to epsilon. So inside matter, there is no charge or free current. We can write these equations if medium is linear and homogeneous. Then the Maxwell equations can be written as del dot E equals to 0, del dot B equals to 0, del cross E equals to minus curl B by curl T, and last one del cross B equals to mu epsilon curly E by curly T. So if we have to write the refractive index, then this is equals to epsilon mu upon epsilon naught mu naught, and as for most of the materials, mu is very close to mu naught, therefore n is approximately equals to root epsilon r, where epsilon r is the dielectric constant. So similarly we can write the energy density. U is equals to 1 by 2 epsilon E square plus V square upon mu, and Pointing vector S is equals to 1 upon mu E cross B. And for monochromatic plane waves, frequency and wave number are related by omega equals to K into V, and hence intensity I is equals to half epsilon V E naught square. V E naught square. So this is the expression for intensity. So when a wave passes from one transparent medium into another, we get a reflected wave and a transmitted wave, and the details of this depend upon some electrodynamics boundary conditions. So now we're going to derive these boundary conditions. Boundary conditions. So in general, the fields electric field, magnetic field, E, B, D and H, these are discontinuous at the boundary, and it carries a surface charge density sigma and current density K. So these discontinuities can be deduced from Maxwell's equation in their integral form. So in integral form, Maxwell equations are surface integral of d dot dA equals to total charge enclosed, and second one is surface integral of B equals to 0 for any closed surface S, and third equation, line integral of E equals to negative time derivative of surface integral of magnetic field, and fourth one, line integral of H equals to total current enclosed plus time derivative of surface integral of d. So for any surface S bounded by the closed loop P. So we have to find the discontinuities using these equations. So for equation 1 we consider a thin wafer, tiny wafer, thin Gaussian pillbox. Here we're drawing. And this dotted surface is for below the surface. Okay, so here area is A, and here surface charge density sigma F, and this dotted surface is for D2, and this surface is for it's for D1. Okay, so our first equation becomes d1 dot a minus d2 dot a equals to sigma fa. As the sigma is surface charge density per unit area, so total charge can be written as surface charge density per unit area into area. So this equation becomes d1, and the edge of the wafer contributes nothing as the thickness goes to 0. So the component only perpendicular to the interface is discontinuous, that is d1 perpendicular minus d2 perpendicular equals to sigma f. So d is discontinuous. This is our first boundary condition. So similarly, second equation gives us the result b1 perpendicular minus b2 perpendicular equals to 0. So this is a second boundary condition, and which tells us that perpendicular component of magnetic field is continuous. So now third equation. For third equation we have to consider a thin Amperian loop. So length of this is L. Length is L. So again we have two surfaces, and this is our unit vector n cap. So equation 3 becomes E1 dot L minus E2 dot L equals to negative time derivative of surface integral of E, that is a magnetic field. Again in the limit width goes to 0, so we have E1 parallel minus E2 parallel equals to 0. This is our third boundary condition, which tells us that parallel components of electric fields are continuous. And finally fourth equation implies H1 dot L minus H2 dot L equals to total current enclosed. Okay, so no volume current density will contribute, only surface current, and n cap is a unit vector perpendicular to the interface. So n cap cross L is normal to the loop. So total current is equals to Kf dot n cap cross L, and if we replace the dot and cross products, what we get? Kf cross n cap dot L. So from here H1 dot L minus H2 dot L equals to Kf cross n cap dot L. So finally what we get? H1 parallel minus H2 parallel equals to Kf cross n cap. This is our fourth boundary condition, and parallel components of H are also discontinuous. So in terms of electric field and magnetic, that is E and V, these equations can be written as epsilon 1 E1 perpendicular minus epsilon 2 E2 perpendicular equals to sigma F V1 perpendicular minus V2 perpendicular equals to 0. Third one, E1 parallel minus E2 parallel equals to 0. Fourth, 1 upon mu1 V1 parallel minus 1 upon mu2 V2 parallel equals to Kf cross n cap. So in particular, if there is no free charge or free current at the interface, then these equations become epsilon 1 E1 perpendicular minus epsilon 2 perpendicular equals to 0. V1 perpendicular minus V2 perpendicular equals to 0. E1 perpendicular E1 parallel minus E2 parallel equals to 0, and fourth one 1 upon mu1 V1 parallel minus 1 upon mu2 V2 parallel equals to 0. So these are four boundary conditions which are the basis for the theory of reflection and refraction. So these equations just relate the electric field and magnetic field on the two sides of the interface. So we use these boundary conditions to find the reflection and transmission at normal incidence. Okay. Reflection and transmission at normal incidence. So here we suppose that xy plane forms the boundary between two linear medium. A plane wave of frequency omega traveling in the z direction and polarized in x direction approaches the interface. So we have a incident wave, so first of all we have incident wave. These are the components EI, velocity V1 and VI. So wave when reaches a interface, it reflects the components For that reflected wave, velocity remains v1 same, er and br. So this is first medium and this is second medium, and there is also transmitted wave that goes to the next medium. So et, v2 and v3. So incident wave equation can be written as ei. The symbol, as we discussed earlier, represents complex function. So ei z equals to e naught I exponential iota k1z minus omega t bi 1 upon v1 e naught I exponential iota k1z minus omega t, and it gives rise to a reflected wave er equals to e0 r exponential iota minus k1z, because direction reverses, minus omega t so here this is in x direction, and magnetic field is in y direction, and also here in reflected wave electric field is in x direction, and Vr equals to minus 1 upon V1 E0 R exponential iota minus K1Z minus omega t y cap, and it travels back to the left in the medium 1, and the transmitted wave Et equals to E0 t exponential iota k2z minus omega t x cap and dt b0 t exponential iota k2 z minus omega t y cap. So these are equations for incident, reflected and transmitted waves. Okay, so minus sign in BR is by the fact that the pointing vector aims to the direction of propagation. So at z equals to 0, the combined fields on the left, that is E I plus ER and BI plus BR, must join the fields on the right, and ET and BT in accordance with the boundary conditions. Okay, so in this case there are no components perpendicular to the surface. Okay, so now we are applying the boundary conditions which we have proved above or find above. So we can write it here: epsilon 1 E1 perpendicular equals to epsilon 2 E2 perpendicular. Okay, this is first boundary condition. Second boundary condition is B1 perpendicular equals to B2 perpendicular. Third one is E1 parallel equals to E2 parallel, and fourth one is 1 upon mu1 V1 parallel equals to 1 upon mu2 V2 parallel. So these are boundary conditions. Okay, so as we have no perpendicular component, so equation 1 and 2 are trivial. Now equation 3. So this equation 3 requires that equation 3 so third boundary condition, that is E1 parallel equals to E2 parallel. So here we have, on the left side we have EI ZT plus ER ZT equals to, on the right side we have transmitted wave ET ZT. So putting the values, E0I exponential iota K1Z minus omega t, can write it again, exponential iota K1Z minus omega t. Okay, so plus E0R exponential iota minus K1Z minus omega t. So this is equals to E0t exponential iota K2Z minus omega t. Okay, so as we are considering at it as at z equals to 0, so above equation becomes E0I exponential iota 0 minus omega t plus E0 R exponential iota 0 minus omega t equals to it. Okay, so this is equals to E0t exponential iota 0 minus omega t. Okay, so it becomes E0I plus E0R taking common exponential minus iota omega t equals to E0 t exponential minus iota omega t. So from here we get the equation E0I plus E0 R equals to E0 t. Okay, so this equation we will get this from where by using equation number 3, that is boundary condition 3. Now we have to find the boundary condition. We have to find the next equation using boundary condition 4. So boundary condition 4 implies 1 upon mu1 V1 parallel equals to 1 upon mu2 V2 parallel. So again putting the values, 1 upon V1 E0I exponential iota K1Z minus omega t minus 1 upon v1 e0 r exponential iota minus k1z minus omega t. This is equals to 1 upon mu 2 1 upon v2 e0 t exponential iota k2z minus omega t. So again we are considering this equation at z equals to 0. So it becomes 1 upon mu 1 1 upon v1 e 0 I exponential iota 0 minus omega t minus 1 upon v1 e0 r exponential iota 0 minus omega t equals to 1 upon mu 2 1 upon v2 e0 t exponential iota 0 minus omega t. So from here what we get? 1 upon mu 1 v1 e0 I minus e0 r into exponential minus iota omega t equals to 1 upon mu 2 v2 e0 t exponential minus iota omega t, and from here we get second equation e0 I minus e0 r equals to mu 1 v1 upon mu 2 v2 e0 t. So it becomes e0 I minus e0 r equals to beta e0 t. So here beta is equals to mu 1 v1 upon mu 2 v2. Now we are solving these two equations. First equation is e0 I plus e0 r equals to e0 t. So solving e0 I plus e0 r equals to e0 t. The second equation is e0 I minus e0 r equals to beta e0 t. So adding this cancel out. So from here we get the value of e0 t equals to 2 upon 1 plus beta into e0 I. So first we multiply the equation 1 with beta. Beta e0 I plus beta e0 r equals to beta e0 t. Second equation is e0 I minus e0 r equals to beta e0 t. So when subtracting, this term cancel out. Here we have 1 minus it's beta minus 1 beta minus 1 e0 I plus 1 plus beta E0 R equals to 0. So E0 R is equals to 1 minus beta upon 1 plus beta into E0 I. Okay, so here we have beta equals to V1 upon V2. So we can write these equations in terms of velocities also. So in terms of velocities, these equations are E0R equals to 1 minus beta 1 upon beta 2 upon 1 plus beta 1, sorry, V1 upon V2 E0 I. So it becomes V2 minus V1 upon V2 plus V1 into E0. And similarly, E0T is equals to 2V2 upon V2 plus V1 into E0I. So these equations are identical to the case of string. So in that case, reflected wave is in phase. So if here two cases arises, if V2 is greater than V1 and out of phase, and if V2 is less than V1, the real amplitudes are related by E0R equals to V2 minus V1 upon V2 plus V1 E0I, and E0T is equals to 2V2 upon V2 plus V1 into E0I. So ratio of the reflected intensity to the incident intensity is represented by R, that is IR upon II, and I is equals to half epsilon V E naught square. So it becomes E0R square upon E0 I square. So we can put the value of velocities in terms of refractive indices. So these equations are N1 minus N2 upon N1 plus N2 square E0 I square upon E0 I square. So it becomes N1 minus N2, that is R is a reflective coefficient, upon N1 plus N2 square. So similarly, transmission coefficient T is equals to IT upon II, and on solving it becomes 4 N1 N2 upon N1 plus N2 square. And you can easily solve it, that R plus T is equals to 1. So this presents a conservation of energy. So here you can easily prove it by putting the values N1 minus N2 square upon N1 plus N2 square plus 4 N1 N2 upon N1 plus N2 square. So this is equals to 1. So this is all about